Okay, is screen is recording? Hello? Is screen recording, Mr.
Yes, sir.
Awakar?
Yes, sir.
Okay, good. What we'll do, we'll derive two formula. One is if fluid element have a linear deformation, then what would be the equation of the fluid motion? Other one, if there is angular deformation in the fluid and there is rotation, then what will be the equation of motion of the fluid particle that we'll derive today. So at first to derive this one. It's called linear translation and linear deformation. And we already discussed this a little bit, almost halfway in the, I think yesterday, right? So let's see. Over here is the MathCAD file. Okay, we need to start it from here. So we discuss it a little bit and we'll discuss again today. Let's see. Let me copy this picture. Okay. At first, let's discuss this figure, then it will be easier to understand for you. Okay, so you see this one is the fluid element, and we are doing 2D, but actually this fluid element, actually it has a 3D. We are looking only these phases. Then similar thing will happen in this phase, also in the vertical phase, okay, X and Y axis, X, Y, and Z axis. But right now we are looking only deformation along X axis, that what will happen. So this fluid element, it don't is rectangular size. And along X axis, it has velocity U, Y axis, velocity V. But right now we are dealing with only velocity component along X axis. So at point O, this fluid element has a 4 corner. O and B both has the same velocity U. So they are traveling with same speed. After time delta t, they came in right over here. So what will be the distance from point B to this position? How much the distance? Obviously velocity into time. So that distance is this one, u into delta t. Because with delta t time, this fluid element travel from this point to this point, or line OB came in the new position. So this is u delta t. Now, line, why this fluid element deform? Because line AC is travel faster than line OB. How much faster? At point B, velocity is u, but UVW all also changing respect to change of distance. So u, how much it is changing along x-axis? This length S length is delta x. So by using Taylor series, our H will be delta x, right over here, delta x. So velocity of C, point C and A along x-axis will be this one. This is derivative of the function, this is the H. So u plus del u by del x into x, del x. Now, he traveled from where? This line originally right this point, but it's travel right over here. So how we'll get this distance? Obviously, this velocity into delta t. That is we are showing right over here. Now, our intention is to figure out the deformation. Deformation means how much dimension change. If you got the delta, that means change of dimension, then you can figure out the strain. So our intention to change the amount of length. So this much length is increase of the fluid element, right? So how we can figure out this distance? We already know distance from this point to this point is this one. So how much distance from here to here? We just add the delta x because this portion length is delta x. So you put delta x over here. So right now we have the distance from this point to this point. Similarly, we already know distance from this point to this point, delta ut. Now, how I can figure out this distance? So total this distance and subtract this mass. If I make one more line, this mass. So line CA is we are taking a imaginary line. That this is delta x, this is delta x. So distance from here to OA is u into t plus delta x. So from bottom distance, you subtract this one, you subtract this value and this value, you will get this one. So that's what we did. You see right over here looking right. We need to figure out distance A prime. So we took line OA prime from O to right over here. How much distance? Delta x plus this one. So this distance into t. Minus, we subtract this one and this one. Ut minus delta x. So after, if you simplify the equation, del x will be out, the u delta t will be out. So this mass length is increase. That is called linear deformation. That means if you look in the solid mechanics, you get epsilon equal to delta by L. Strain. Now, so we got delta. How will figure out the strain? Linear strain equal to deformation divided by original length. So we are getting del u by del x into delta t. Delta x will be out, right? This is linear deformation. How we can figure out the strain rate? Strain rate mean is coming based on deformation. And to get that deformation, how long take time? You divide by that time, you will get strain rate. So rate of deformation, this is the delta linear strain, I'm sorry. This is the strain, and this strain is happening within time delta t. So we'll figure out the linear strain rate, that means divided by the time along x-axis, epsilon xx equal to limit delta t, because delta t time is very small, close to the 0. So we divide by del t del t will be out. Then this is coming equal to this one, del u by del x. Similarly, along y-axis, deformation will be this much, strain rate. Along z-axis, this much. So this fluid element, actually it is a cube, right? It is a cube. So its size is increased along all axes. Along x-axis, it become this mass length increase, say this mass. Similarly, along y-axis, it was this mass, he increases along this mass. Along z-axis, it was this mass, but he increased this mass. That means his volume is increasing within time delta t, because strain rate. So how we can figure out the volumetric strain? We know along x-axis, strain rate this much, y-axis this much, z-axis this much. So if you summation of these three, then we can figure out the volumetric strain. Volumetric strain means change of velocity dV divided by original V, right? Then this term again you divided by time dt. This is called volumetric strain. So it actually, if you rearrange this one, it will come 1 by V dV by dt, that coming material derivative. In terms, we can write down this way. This equal to summation of all these three. So you get this one, okay? Now we can express this one with simplified form. So volumetric strain, this one we can express with the deep B. If we know vector V equal to this one, velocity vector. And divergent vector is this one. If you make the dot product, then these two will get this one. So this one, in short, you can say divergent of V. So for incompressible flow, volume is not changing, right? In that case, what will happen? This term will be 0. So it's coming, we can put 0. That means divergent equal to 0. So if I give you some equation of U, V, W, and you check it, the flow will be compressible or incompressible. How we can figure out? You satisfy this equation. If you satisfy this equation, then flow will be incompressible. If it is not satisfied this equation, that means summation of all three is not coming 0. That means the flow is not incompressible. Okay. What I can do, I can say, I can give you, let me just write down instead of typing, that will be easier. I can say V equal to x square plus y into I, vector I, plus I can say one more, the z square plus x square into vector j, and one more vector k, right? We can say into z square plus xy into k. And you prove it, the flow is compressible and incompressible. How can do it? Where U equal to this, V equal to this, W equal to this. Then you just figure out the derivative and substitute here. You satisfy this equation, then you can say this is incompressible flow because volumetric strain is 0. If it's not 0, that means flow is compressible, and you figure out the amount of volumetric strain. Okay. Any question from here?
No, sir.
Anyone? No? Okay. Okay, next slide, we'll figure out the rotation of the fluid element. Rotation, other one is right over here, angular deformation of the fluid particle. Okay. Okay, just think what I am saying. This is the fluid element at time t, point coordinate of point O is xy, and side length is delta x, delta y. So this is 2D. Point O has velocity u and v along y-axis, u along x-axis. And after time delta t, this element coming right over here. So what does it meaning? That line O is coming right over here. Okay. So E point O has a velocity u. Velocity u, how much will be this distance? U into delta t. Velocity of x component into delta t. What do you say? Why coming like that? Because you have t component of velocity. Velocity u and velocity v. If it has only no velocity along y direction, then what will happen? Then O will travel horizontally instead of going like that. But if y is going like that, it has a some velocity component along x-axis, along also y-axis. So how much the distance he travel along y-axis? You can easily figure out velocity along y direction into time. So that distance, vertical distance traveled by line O is delta V into delta T. V is the y component velocity. Now, y point B, he is supposed to stay right over this point, but instead he travel more distance than point O. What is the reason? Along x-axis, right? What is the reason? Anyone? Because O traveling with velocity u, but B traveling with higher velocity, and his velocity is not the u. If right over his u, what will be velocity at point B? We can easily figure out by Taylor series. That will be u and u changing velocity along y direction. So that will be del u by del y. This is not v u, okay? Del u by del y into a's. So your a's in that case will be y. So that's why B travel more distance than point O. Now easily you can figure out this distance from here to here. This much distance travel by point B. So what is the delta eta, zeta, this value? You can easily figure out this distance minus this distance. Similarly, you see point A. A supposed to be right over here, right? Right over here. But he travel along y direction more, y from this point. Because at point O, your y velocity is v, but right over here is no more v. Is travel faster than point O. What is this velocity? That will be v, and v is using Taylor series, changing along x direction, dv by dx into h. What is the h? Del x. You put del x over here. Okay. And this velocity multiply by the time, then you will get this much distance from here to here. And this distance subtract this one, you'll get del eta. Okay, so let's see, we can derive. Then we can figure out this delta beta and delta alpha. That means it's called angular deformation. How much angular deformation is there? Okay, so we can derive it. Have to go through the mathcat file. That will be easier. Okay, you can see the file.
Yes,
Hello?
sir.
Okay. So what we are saying, a rectangular fluid particle has a velocity uv, vector v, and it's moved from point O to O prime within a infinitesimal time, delta t, as shown, figure like that. Okay. So this one is called zeta, this letter, and the bottom one is called eta. Okay. So you see at time delta t, point O moves to this point, O prime. Horizontal distance traveled by point O will be equal to how much? X velocity into delta t. So that is coming from here to here. That is showing in the upper, right over here. Okay. Now, horizontal distance traveled by point B will be how much? That we need to figure out. So horizontal distance traveled by point B, you see point B velocity will be this one. Velocity is this one, point B. U plus del U by del Y into del Y. Because at the point O, our velocity is B, but point B is traveling faster than point O. So we need to figure out that what will be the velocity at point B. We don't know, but we know the velocity, magnitude of velocity at point A. So how much the distance is del Y in Taylor series, okay? So you can figure out the velocity at del Y will be how much? That means H will be del Y. So it will be U function of fx, right in the equation, this one, U, and del f by del x. In our case, y-axis is the x-axis. You are working with the y-axis, derivative will be del y, not x. And h is del y, so you put del y. So this is your distance traveled by point B. Now, what is the zeta? So this blue distance traveled by point O, right? So distance traveled by point B from here to here equal to this one, delta t. So this distance minus this distance, you'll get zeta. So zeta equal to velocity of B into time, you get the distance, minus distance traveled by point O, right over here. So minus ut, finally you are getting this one, okay? Now, similarly, we need to figure out this eta. Again, in vertical direction, distance traveled by point O, V into delta t, this mass distance. So what is the velocity V at point O? I'm sorry, at point A. Again, you need to use by Taylor series. At point A, velocity will be V del V by del X into del X. So this is the df by dx. df by dx is this one. And h is del x. So this distance from here to here will be how much? Y velocity of point A into time. So Y velocity of point A is this one. So times by time, delta t, minus distance traveled by point O. So you are getting this one. Okay. So we are getting now, you see, what is our intention? Angular deformation. We try to figure out this angle, del beta, and also this del alpha. If I apply tan, I know the perpendicular distance, this one. Tan alpha equal to perpendicular by base. That means this eta divided by this distance. Okay. Now, this angle we will consider very small. If this angle is very small, then what will be the length of OA or length of this mass? What I'm saying, what will be the length of this mass? If this angle is very small, then we will think that when they are moving little smaller, we'll think that this length right over here will be same as delta x. That is simplification. We are sacrificing the accuracy. Again, if del beta is very small, then if I draw a triangle, this will be del zeta, but this distance, that means vertical distance from here to here, we are thinking is same as del y. So tan beta will be del zeta divided by del y. And tan alpha equal to del eta divided by del x. So we get this one. Now that tan alpha equal to del eta by del x. Now if this angle is very small, then we can say tan alpha equal to only alpha. You figure out, you fall very small angle, you put in the calculator 0.005 degree, you see what value is giving you, same as the magnitude of the angle. You make sure you take it in the radian. Okay. So we are getting del alpha equal to this mass and del beta equal to this mass. This is the angular deformation. Okay. Now this eta value is how much? We already figure out this is value of eta. So you put eta at the top, del x is right over here. So you got del v by del x into this term. Okay. Similarly, in the del beta, you put this value. What is this value? We already have it, this one. So you put there, then you are getting del u by del y into t. So what is our total shear strain in the fluid element? Shear strain means angular deformation. So you need to add these two angles, del alpha plus del beta. So this mass is the angular deformation or shear strain. So angular deformation, if his angle is gamma, gamma mean you have to make summation of del alpha deformation in along y direction and along in x direction. So then you say, now this mass rotation is happening along which axis? Anyone? This mass rotation is happening in xy plane, but the rotation is along z axis, perpendicular to the computer screen. Okay. So that means if I say angular deformation is gamma, I will say gamma dot xy. Why gamma dot? This is the angular deformation, amount of deformation or amount of angle and happening within what time? Within time delta t. So you divided by delta t, that will be strain rate, shear rate of shear strain or rate of angular deformation if you divided by the time. So gamma dot xy equal to limit dt tends to 0, you have this value. Now you just substitute two value, gamma y, gamma del alpha, del beta, then value is over here. Okay, you divided by the time, then time will be out. Okay, then you get actually this one. Okay, similarly, if you like to figure out the rotation of the fluid element along xz plane, then you got this one. Along yz plane, you get this one. Very simple. Gamma xy, gamma dot xy. So you will have x, derivative x, and you have to take velocity y, del v by del y, plus then you derivative del y. You divided by del y in the bottom, and your velocity has to be other axis, that means del u. Then gamma xz, at first you take gamma del x. What is the other axis? Z, velocity component w. So in the top will be del w. Plus this, for this one, you already take derivative x, you take derivative now z. So del z, what is the other axis? X. So you take velocity del u. Similarly, you figure out gamma yz. Okay. So that means this deformation, angular deformation, this one along z axis, and this one along y axis, this one happening along x axis. So the rate of angular deformation is related to a corresponding shear stress, which causes the fluid element change in shape. If there is this kind of deformation, then fluid element will change their shape. That's why sometimes you see fluid element is rotating. There is a deformation in the fluid element. Now, if we took, try to figure out the rotation, gamma, omega equal to this one, dv into v. dv into v equal to half curl v. This one is also called curl v. Okay, and what is the div? This is the div and this is the v. And if you take the cross product of these two, we get w equal to div divergence of v, cross product. The cross product of v is called curl. And this, if you have cross product, still you have a vector, you will have this one. Okay, write this one. So for rotational flow, what will happen? Rotational flow occur due to the viscosity of the fluid, because viscosity causes fluid to shear deformation. But if there is no deformation of the fluid element, what will be the magnitude of this one, this value? Anyone?
0.
That will be 0. That's why we'll say for irrotational flow, curl of V equal to 0. So anytime, if I give you a equation, like I'm saying vector V of the fluid element, some function like x, y, z, I is over here, then some function into j, then some function into vector k. So you can figure out what is the u, small u, what is the small v, what is the small w. Then I say figure out is flow is irrotational or rotational. you figure out this vector. Then it's coming 0, that means flow will be irrotational. Is not 0, then there will be rotation or vortex in the flow. So you see curl V is 0, then flow is irrotational. Now, there is a one definition we use in the, is called vorticity of the fluid. What is the vorticity of the fluid? 1 second, the misspelling. If you take twice of curl, angular velocity, angular deformation, you multiply by 2, that term is called vorticity. That means curl of V, if you figure out curl of V equal to 2 into angular velocity, 2 into omega, right? This 2 into omega, this term is called vorticity of the fluid. If this vorticity is 0, then there is no angular deformation, no rotation of the fluid. And this vorticity is not 0, that means there will be some rotation in the fluid element. There will be some vortex. Okay. So vorticity zeta equal to 2 into omega. Okay, or curl V. So just sometime we put short question that what do you mean by vorticity of the fluid element? Okay. So far, any question from here? Anyone?
No, sir.
No. So right here we figure out the angular deformation, right, of the fluid element. Now there is a one thing happen that is called rotation of the fluid element. But you don't have to scare. We'll use the same figure, but we'll figure out the rotation of the fluid element, how much rotation is happening. And you see right over here, the SOA, he rotate along anti-clockwise direction, right? That's why he's supposed to be over here, but he's rotated along anti-clockwise direction. And line OB is supposed to be here, but he rotated clockwise direction. So from here, we can figure out the rotation of the fluid element. And how we can figure out the rotation? You need to figure out the angle alpha and beta. And we already did from the previous derivation right over here. We did figure out the angle right over here. But what is our angular rotation? Now, in that case, if line OA rotate along clockwise, anti-clockwise, so his rotation is positive. And line OB rotate clockwise, so his rotation is negative. So we can say angular rotation, and this rotation happen along which axis? Rotation is, this is the x-axis, this is the y-axis. That means rotation is happening along z-axis, right? If I say this is the z-axis, this is my x-axis, this is the y-axis. So you are rotating something this plane, that means he is rotating along z-axis. So this rotation right over here will be angular velocity or angular rotation along z-axis. And that one will take half average. We'll take average of del alpha minus del beta. And finally, we will get del b by del x minus del u by del y. Now, you might have a question, the why we know the question. Because we have to keep similarity with previous formula. If you figure out the rotation along z-axis, that will be how much? 2 into omega z, okay? Like coming 2 into angular velocity equal to vorticity. or you can just remember we are taking the average angular average rotation. So this is the rotation along z-axis. Similarly, what will be the rotation along y-axis is this one, along x-axis will be this one. And z-axis, how will figure out? If you write over here is x, y, z. You going rotation. So I need to figure out omega z. You take half, we have to take the average into derivative. Which one you will take? You have to take derivative x first. After z, you are getting x. So del v, you say del x you take. Now you are taking rotation along z-axis. That means velocity component will be other two axes. So velocity component will be x-axis u and y-axis v. So in the bottom, you are taking derivative del x. So the top will be del v minus, then bottom you have to take del y. Del x you already take. And velocity component will be x-axis, then del u. Similarly, if you look in the x, you are taking rotation in the x, then you have to consider this y and this z. Okay, velocity w along z-axis. So you take formula half, that means you are taking average. You are try to x-axis, right? So after x, you get y. So you take del y. Now you try to figure out angular velocity along x-axis. So you have to take velocity v and w. You take already del y, so over here will be del w. Then minus other axis del z and velocity y-axis del v. So it's easy. So you need to remember the sequence. Now, if you like to figure out the total angular rotational vector, then will be omega x into omega y into omega z. Then you will get this one. Okay. So this one again, you can express in terms of divergence, then equation will be this one. Now, if there is a no rotation along z-axis, then what will happen? This term will be 0. That means fluid element, this is omega z, right? Fluid element rotate along x-axis and y-axis. If this one is 0, that means omega y is 0. The rotation will happen along x-axis and z-axis. If all them 0, then there will be no rotation in the fluid element. Okay. Okay, we covered it. Any question? Any question?
No, sir.
No question? Okay. So let's go back to our slide. This one we already derived it. Now we just summarize some equation over here, that this is the vector component of velocity. This is the del operator. You learn from the math. What is our continuity equation? This one. In short form, this one, because this equal to actually this one. Then for incompressible flow, your rho is constant, so this will be 0. Then contraindication become this one, or you can say this one. This one will be 0. This equal to, then you can say 0 is the contraindication. If flow is rho is constant. And continuity equation in cylindrical coordinate, you just remember the equation, memorize, and you need to know what is the VR, what is the V theta, what is the VZ, what is the rho, and what is the R. Okay. And what is the volumetric strain? We already figure out volumetric strain equal to, this is volumetric strain equal to this one. Okay. 1 second. So for incompressible flow, if flow is incompressible, then there will be no volumetric strain. Volume will not increase. So you'll have this one mean this equal to 0. Okay. And you see this one is part of continuity equation. If you see for incompressible flow, you get the same equation. So what does it mean? If a equation satisfy continuity equation, this one, that means there will be no increase of volume of fluid or no deformation of volume. Volumetric strain will be 0. So both are the same condition. Okay. Then in case of rotational flow, what is our vector equation is this one. And what is omega x? This is my omega x, this is omega z, and this is omega y. And verticity equal to 2 into rotational vector or curl V, divergent into V, cross product of two vector. And this rotational vector also we can express in terms of curl, half into curl of V. And angular deformation, you need to remember this formula. Angular deformation in XY plane is this one, YZ plane is this one, and XZ plane is this one. Okay. And when we will solve some problem, then it will be easier. You can easily figure out. Okay. So we need to stop it here. Okay. One thing I like to share with you that your section B, section A, right?
Yes.
Do you have
Yes, sir.
class on Sunday? Sunday we have class with section B from 8:50. You can join with them or you have the class.